Yeah. So, thanks for coming. Yeah. I hope I'll try my best to keep your interest alive till the end. And yeah, please cooperate by stopping me and asking questions whenever you tend to lose me. Yeah. So this talk is based on, as Palash said, joint work with Arkadev Chattopadhyay. He is at TIFR. Jai Kumar Radhakrishnan. He was at TIFR until recently, has now moved to ICTS, Bangalore. Nikhil Mande is currently at University of Liverpool. He was a graduate student at TIFR, which is where I met him. And Yogesh Dahiya. He is a graduate student at IMSC, Chennai. Okay, so I'll spend a lot of time explaining to you the setup and the background, and then tell you the specific question that we ask and the answers that we offer. Yeah, so the basic object of study is Boolean functions, which are like familiar objects. They look like this. Yeah, so it is an assignment of a bit, a 0 and a 1, to each input of a certain size, if each bit string of a certain size. So there are 3 in this case. In general, there will be n Boolean variables. I'll denote them by x1 through xn, and I'll refer to this string as x. Yeah, so x is going to stand for this vector, and fx will denote the bit in the last column of the xth row of this table. Yeah. So in its full generality, some of these entries are unfilled, and you will put some notation to just indicate that the function is not specified in these positions. They are called don't care conditions. But the functions that we'll consider in this work are total functions, where you have a bit in each position. Yeah. Actually, the questions that we'll ask seem to, be very uninteresting for functions with. So they make sense only for functions which are completely specified. We'll see that later. Yeah. So now so a Boolean function is specified explicitly. They can be specified explicitly just by listing the input for every, listing the output for every input string. But it could also be specified. Some Boolean functions admit a more succinct representation. So I'll tell you a few of those which play a central role in Boolean function complexity, and also I'll convey some of the concepts here through these functions. So these are like familiar examples. Here. So AND of x1 through xn is 1 if each xi is 1 and 0 otherwise. OR is 1 if at least one of the xi's is 1 and 0 if all the xi's are 0. Okay. So here is what is called the indexing function. So it is a function of k plus 2 power k inputs for some k. Yeah. Yeah. You may have. So this is often called the multiplexer function in switching theory, for instance. Yeah. And what is this? Basically, yeah, there are these k bits s0 through sk minus 1, and then 2 power k bits z1 through z2 power k. And so there are k plus 2 power k inputs in total. So the number of input bits is this, and its value is the following. The first k, the s bits, uniquely pick out one of these 2 power k z's. Yeah. So there are 2 power k combinations for k bits, and so that will serve as an address for one of these 2 power k bits. Yeah. And the value of the corresponding z bit is the value of the function. So I'll just write it as so I'll refer to the first k bits as s and the next 2 power k bits as z. So s and z are vectors. Yeah. And so these k bits serve as an address for one of these 2 power k locations, if you like. Yeah. And you look up the corresponding z bit, and that is the value. Example. Yeah. So let's say k is equal to 2. So then 2 power k is 4. So s0, s1, z1, z2, z3, z4. Huh? S0, S1 and Z0. Okay, let's see that. So Z0, Z1, Z2, Z3. Yeah? Now let's say S0 and S1 are 0, 1. That is the binary of 1. So you look up Z of 1. And yeah, the value of z1 is the output of the function. Yeah. So the combination of S0 and S1 is a binary representation of one of these 4 numbers, 0 through 3.
So if it was 1, 1, then
Z3 would have been the answer. Yeah. Yeah. So
there is the index of Z. S0, S1 is the index of which Z should be.
Yeah. Exactly.
The value of Z.
Exactly. Yeah. Yeah. So this is the multiplexer function, yeah, or the indexing function. There is one more function that I'd like to tell you about before moving to other things, is what is called tribes. So the function is given by a Boolean circuit, which looks like this. So it's OR of AND. Yeah, each AND gate has fan-in square root n. Fan-in is the number of inputs, and the variables that feed into the AND gates are a disjoint set of variables feeds into each AND gate. Yeah, so there are n variables in total, and they are partitioned into square root n blocks of square root n variables each. And yeah, the AND gates in this level compute the ANDs of the respective sets of variables, and then yeah. It's called tribes. Yeah, this comes from voting theory. Yeah, so it's some sort of a strange district level election. Yeah. So, okay. So yeah. So these are Boolean functions, and these are sort of succinctly represented. From these descriptions, you can write out the truth table of these functions. Truth tables are often written as a 2-dimensional grid, and they are referred to as K maps, which you may have seen in switching theory course. Yeah, I'll make reference to these sometimes because I thought that many of you will be familiar to this. You may have seen them in Vivas, for instance. And yeah, so but if you don't remember, then don't worry. Yeah, just ignore all those references. So this talk is about very yes.
So this just to understand, describe this function. This value will be 1 only if at least one of the root n sized blocks have all ones.
Yes, exactly. Great.
It's just a DNF, right?
It's a DNF, but with a very special structure. The terms are all disjoint and so on. Yeah. And have same width. Yeah, so I'll talk about decision trees. So a decision tree is a very simple computational model for computing Boolean functions. So Boolean functions are seen in courses of computer hardware maybe, but they serve as a general model for capturing decision tasks. Yeah. So this a table sort of encodes a decision input-output behavior. Any object that can be stored in a computer can be encoded by a bit string. Yeah. So yeah, and then this column indicates a binary decision that you make about each input. Yeah. So let me talk about decision tree. So let me tell you what a decision tree is through an example. Yeah. Okay. So this is a decision tree that computes AND function of 3 variables. Yeah. So what does it do? So it's a binary tree. It's a full binary tree. So a node is either a leaf or has 2 children. Yeah. There is no node with 1 children. So it's a full binary tree, and each internal node is labeled by a variable, and each leaf is labeled by a bit, a 0 or a 1. And given an input x1, x2, x3, you can sort of run this tree on that input as follows. So you start from the root and consider the variable that is which is the label of this root, and you query that variable. So you assume that this string is held by an oracle to whom you can issue queries, and whom you can ask for values of individual bits. So you ask the oracle what is x1, and the oracle responds with a 0 or a 1. So let's say the string is 1, 0, 1. So if x1 is 0, so there are 2 children, one corresponding to, there is 1 children corresponding to each response to the oracle call. So if x1 is 1, then you will come to x2, because you will take this edge which is labeled by 1. And then you will query the oracle, query x2, because x2 labels this node, and the oracle will tell you that x2 is 0. So then you will come to this leaf. So you come to this child of x2 and realize that it's a leaf, and it's labeled by 0. So the computation stops here, and you output the label of this leaf, which is 0. On the other hand, if x2 had been 1, you would have taken this path and then queried x3, come here, and would have then reported 1 as the output. Yeah. So this is called a deterministic decision tree that computes the AND function. Yeah. Now I would like to talk about the complexity. It's an algorithm that computes a Boolean function, so I'd like to talk about its complexity. So there are. Yeah, please ask.
Is it general?
Meaning?
Can it compute all Boolean functions?
Yeah, for any Boolean function, you can write down a tree that queries all the variables, full binary tree.
Okay.
And then label the trees, basically write the truth table at the bottom of the function.
The reason I'm asking is because with 3 Boolean variables, you have got 8 rows, but you have only got 4 boxes.
Yeah, but for AND functions, so this corresponds to many rows. This corresponds to all the rows for which x1 is 0. So this actually corresponds to 4 rows.
Right. So what I'm trying to ask is for this obviously it
Yeah.
works, but for any Boolean function with 3 variables will it work?
For any Boolean function with 3 variables, you can potentially have a more complex tree with.
For any Boolean function with n variables, you will have a decision tree with height n.
Yeah, so, and it's trivially you query all the variables.
The reason is that each variable is basically bisecting the truth table into 2 parts.
Absolutely, yeah. Okay, so I'd like to, as I said, talk about complexity of a tree. Yeah, I'd like to say that, like, I'd like to be able to compare 2 trees and say that one is more efficient and so on. I'd like to be able to compare the trees. So, the complexity measure that has received a lot of attention in the Boolean function analysis community is the depth of the tree. Yeah. So, capital D, let me denote it by capital D of T. So, let's say T be this tree, is the depth of T. So, for this tree, dt is 3. So, yeah. So, depth is 3. Now, another measure that has received an attention in machine learning is the number of leaves in the tree or the size of the tree. And now this is a full binary tree, so the number of leaves in the tree is within a factor of 2 of the total number of nodes in the tree, right? It's a full binary tree. It's basically a proxy for the number of nodes of the tree. So it's this. So let me write D size of capital T. So this D will stand for deterministic. It's the number of leaves of T. Yeah. And now, so the depth is the number of queries that you make in the worst case. Yeah, naturally, yeah, trivially. And size you can, yeah, is the basically, so basically we'll look at log of the size, log of D size, which is the number of bits that you need to write down the name of a node. Yeah. So if you simulate a tree, then you'll need to remember the current node and you'll need that much of extra space. So it stands for space complexity in some sense. Okay, all right. So D of T is the depth of T, and for a function f, D of f is the depth of shallowest tree that computes f. Doesn't have to be unique here. I mean, for and you can query these variables in a different order. You would end up with a tree with the same depth and so on. And similarly, D size of f is the least number of leaves in any tree T that computes f. So for df, it turns out, so a dual degree student of mine has found that given a truth table, there is a polynomial time algorithm to find out df. Polynomial in the size of the truth table, so polynomial into power n. Yeah. D size I don't know, yeah, haven't thought about it. Yeah. So let this be here. Okay. So I've been using the term deterministic. So let me talk about like there are trees which are not deterministic and which are probabilistic. So I'll refer to them as randomized decision tree. So a randomized decision tree is, like, informally speaking. So here, you know, the choice of the variable that is queried in each step is based on the responses to all the earlier queries, right? So here you are querying x3 because earlier you queried x1 and received the answer 1, and you queried x2 and received the answer 1. So this node sort of encodes the entire history from the root. But for randomized tree, in addition, the tree has access to some coins that it can toss and make decisions based on that. For instance, if x1 is 1, then maybe with probability 3/4 it queries x2, and with probability 1/4 it queries x3. On the other hand, if it's 0, with probability 1/9 it queries x1, with 3/9 or 1/3 it queries something, and with the remaining probability it queries something like that. So for instance, I forgot to mention another function here. It's called the majority. So let's say n is odd, and majority of x1 through xn is 1 if there are more 1s than 0s, and 0 otherwise. Now, majority, you can draw a deterministic, you'll be able to convince yourself that any deterministic tree that computes the majority function will query all the variables in the worst case. That you'll be able to compute. But here, consider the following randomized tree for the majority function. Or rather, let's, before getting to that, let me talk a little about, I just realized that I haven't finished the definition of a randomized decision tree. So the randomized decision tree, as I said, makes coin tosses, and there is another view. There is another view of randomized decision trees that we'll adopt here, which is that we'll think of them as probability distribution over deterministic trees. Yeah. So you have, let's say, T1, a bunch of deterministic trees, T1, T2 up to TL, and there are some numbers written down here, P1, P2 up to PL. Each PI is non-negative and they add up to 1. Yeah. So you can think of a probabilistic, randomized or a probabilistic tree as such an object. A bunch of deterministic trees, each having its own number, weight, let's say, pi. Yeah.
These trees can represent the same function or can represent any function?
These trees can represent any function. They don't have to compute the function that you are designing this tree for correctly. Yeah.
So basically any collection of L trees?
Any collection of L trees. No, there are some properties that we'll write down. So such a.
But T1 and T2 can compute
very different functions.
How are you attaching the probabilities to the trees here?
No, I'm defining a randomized tree to be a probability distribution over deterministic trees, and we will say, so this, let's say, I'll call this T and call this object.
But each TI is a deterministic.
Each Ti is a deterministic tree.
Exactly.
Yeah, each Ti is a deterministic tree, and each Ti has a corresponding Pi. Yeah, and this tuple of two L trees and L numbers will be called a randomized tree, and we will say that such a randomized tree computes a function f if the following happens. I'll write it down what it means for a randomized tree to compute a function f. So T computes a Boolean function f if for every input x, so x is a vector, remember. Let me write down and then. Yeah. So I have written probability, so I should tell you there is some source of randomness here. So the randomness is just that you sample one of these deterministic trees from this distribution, run it on x and obtain a bit. Then you check whether this bit that you obtain is not equal to fx. So this is the error probability. So the probability that a random tree from this distribution makes an error on a particular input x is bounded above by 1/3. And that holds for every x. Yeah. So this is a worst case guarantee, not an average case guarantee. It's a probabilistic guarantee, but it holds for every single input. Yeah. Now this.
What is the significance of the 1/3?
Yeah, good question. I'm coming to that. Yeah. So this 1/3 looks a bit arbitrary. So
There is no requirement that T1 T2 may not be the same tree. How different they are.
if T1 and T2 are the same, if T1 and T2 are the same tree, I'll just retain one copy and write P1 plus P2 here. I don't. Maybe.
And they can be very similar.
It can be similar.
So is there something about L? How many trees?
No, there is no restriction on L.
L can be arbitrary.
Huh?
L can be arbitrary.
L can be arbitrary. So the complexity, so this is what it means for T to compute F. This is the definition of a T computing S. Now, so Advai asked about 1/3. So what if I replace it by 1/4? Yeah, so let me address this question a little later. So let me first define the complexity of, so the depth complexity, so I'll use the word R to denote randomized. RT is the maximum depth of all these trees in its support. So max I equal to 1 to L, let me write depth of Ti. And similarly R size of T is again the maximum of the number of leaves of Ti's, yeah, maximum over all I. Yeah, now coming to Advai's question. What if I replace 1/3 by, let's say, 1/100? Yeah. Okay. Now let me finish. So R of F, yeah, the randomized query complexity of a function F is again the minimum R of T for all the T's that compute F. So it's now it can potentially be an infinite collection that your maximum is over. Yeah. There can be an infinity of probability distributions over T.
R of F is over all collections of set of trees.
Over all collection as well as all probability distributions over deterministic trees, R of T. So the maximum is over.
T1, T2, Tn is fixed.
No.
They are also
And R of size is also the max. R size of F is also the minimum size of any randomized tree that computes F. Yeah. Okay. Now, yeah. So let's say.
So when you are doing R of T, max I equal to 1 to L, you are taking another one like for all possible trees.
R size of T.
Another one in just R of T.
Yeah.
In this one.
Huh.
Like, are you talking about a specific object T, or are you talking about
T is this tuple.
okay, so it's specific T, right?
Yeah, for the specific T.
So infinite set of T's.
No. R of F is going to be the minimum of this quantity over all possible capital T's. Yeah.
Okay.
Yeah.
So that power question is also probably, shouldn't this be also parameterized by L?
Well, there is only a finite number of deterministic trees, so you can say that all the deterministic trees show up here with sum of the PI's being 0.
Finite number can be exponential also, no?
Yeah, number of trees is exponential. Yeah, that's true.
No, okay. I'm just saying.
That is not.
I
That's
thought here only trees with non-zero probability are getting listed. Suppose we say that. Is there any restriction that the number of trees with non-zero probability should be sub-exponential or something?
No.
It can be exponential.
Yeah. Yeah. So let me get to Advai's question finally. So now, like in light of these complexity measures, does this choice of 1/3 how important is this? So let's say R of F is, let's say, 5. So if I replace 1/3 by 1/4 and recompute R of F with respect to this new definition, can it be like much larger than 5? Yeah. So it turns out that that is not the case. So this definition is pretty robust to the choice of the constant here. So if you change 1/3 to some other related constant, that can affect these complexity measures by at most a constant factor that you can.
So any constant factor less than 1 word?
No. So this makes sense only when it's less than half. So let me talk a bit about RF versus DF to set up the background, and then if time permits, I'll talk a bit about my work. I'll touch upon it, but I'll state it certainly, but I don't know how much I'll be able to tell you about the way we answer this question. But yeah, it was proved in 1989 that for every function f, Rf is order of df, so df is order of Rf cube. Yeah. So that means R cannot bring you more than a cubic advantage. Like use of randomness cannot bring you more than a cubic advantage. Here, totality is important. Like it's important that the truth table contains all the entries and there is no don't care. For truth tables with don't care conditions, this is false for trivial reasons. Yeah. I wrote down the majority function because I thought I'll tell you very simple randomized tree for majority, but then I forgot. So let me just chip that in quickly. So let's say you are computing majority of 3 bits, x1, x2, x3. So here is a random, so deterministically you will be able to say that any tree is forced to query all the 3 bits in the worst case. Yeah. So for any tree, we'll just adversarially answer the queries and keep the tree waiting till it queries everything. Yeah. For randomized, you just sample one of the bits uniformly at random and query it. 3 bits. So the majority. So if the majority is 1, at least 2 of those 3 will be 1, and then you will sample one of those 2 bits with probability at least 2/3. So you'll be correct with probability at least 2/3. So this is a randomized tree with complexity, depth complexity 1. You query only one variable, and the success probability is 2/3. If you want a success probability of 99/100, then yeah, you do something else.
So one thing I missed, like here you have defined RT, but here you are writing RF.
Yeah, so RT is the complexity of a specific tree, and RF is the minimum complexity of any T that computes F. Yeah. Yeah. Oh, yeah. I just wanted to show you this cute little tree for majority function, 3-bit majority function. Yeah. But I'd like to talk about asymptotics, where I can, here like it's a constant size function, so 3 versus 1 doesn't tell me much. It turns out if I look at majority functions on n bits, then there is no asymptotic advantage. So the randomized complexity is also omega n. Yeah. And in fact, to exhibit a function where RF is asymptotically smaller than DF, like RF is little o of DF, is actually quite non-trivial. Yeah. So let me not. So this function probably appeared in 1986 for the first time, a set of those functions. And yeah, this result appeared afterwards. This is Nissan. This is proven by Noam Nissan in 1989. That DF is order RF cube. Yeah.
But you are saying asymptotically.
Yeah.
Asymptotic over.
N. So I'd like to think of the number of variables as a growing parameter, and so on. Yeah.
And the depth will be log of n.
Depth will be.
There are n variables.
Huh.
The depth will not be.
A nodes.
Depth can for AND function. Size can be 2 power. Size 2 power n, can as large as 2 power n. Yeah. It's non-trivial. Like none of these functions gives you a proper asymptotic separation between RF and DF.
So is there some result for special depths where DF is order of RF?
DF is order of RF. So for all these, DF and RF are asymptotically the same, like DF and RF. Huh?
Is that calculated that these functions, set of functions characterized where DF will be order of RF?
Set of function characterized, yeah, that I don't know. Yeah.
There is no special class of functions that can there are so many nodes.
Sorry, once more.
There is no pattern in the functions where DF equal to RF, but there are examples.
There are examples, yeah. DF equal to RF. Like DF equal to RF asymptotically, theta of RF, yeah. And or majority, all these. For this function, tribes, majority, everything, DF and RF both are omega of n. So they are both full asymptotically. You can prove, yeah. Yeah, and yeah, so Nissan showed that DF is always at most RF cube, which is to say that R is at least a third root of DF, always. So use of randomness can only bring you cubic advantage. In particular, it can never bring you exponential advantage. Yeah. For instance, yeah. And yeah, we show in this work that for every f, d size of f is equal to order of it's not as clean a result as theirs, and there are some log n factors sticking around here. Yeah. But in spirit, it does say that even in the, sorry, I made a mistake. So I should say log, so our measures are the log size, the logarithm of the deterministic and the randomized sizes. Yeah. Yeah, but in spirit, the log d size and log r size are polynomially related. This is what we show. I don't know whether the fourth power is optimal. Probably it's not. All we know is that we don't know whether you actually need these polylog n terms. We know that we need at least an exponent of 2 here. It cannot be brought down to something below 2. These are the things that we know. That's what we can prove. Like we can only prove with these extra log terms. Huh?
I mean that log n is the part which is going to be, which might become exponential. If you just put d size and r size.
If I just take d size and r size, no,
You only get some bad function in terms of n.
that is right. Huh? No, I'm not understanding.
Why you're suddenly taking log?
This is what we can prove. It would have been more satisfying if we could get if we could get rid of these log terms, but we could not. This is the result that we could prove. So, in spirit, up to these polylog n terms, log d size and log r size are polynomially related. This is what we managed to prove. This is what I am saying.
But so that means that d size and r size are actually exponentially related, right?
D size and r size are exponentially related. Yeah.
In n, is that correct interpretation?
D size and so d size is at most an exponential function, some quasi polynomial function of r size basically. Yeah. D size is at most some quasi polynomial. 2 power polylog is quasi polynomial. This is like grows faster than polynomial but slower than exponential.
Right.
Yeah.
But what about n? It is exponential in n, is it?
That depends on the function. So if there is some function for which, let's say, d size and r size are both much small, so log d size and log r size are both much smaller than log n. I do not know whether there is such a function. Then this result probably doesn't give you much. Yeah. That is just too large. So log n cube is too large. This is interesting only when log d size and log r size are like comparable with log n, if something like that. Yeah. So, more questions?
So does it actually mean that as the n grows asymptotically,
Yeah.
your randomized algorithm will get better and better?
No. Like as the n grows, like they correspond to different functions, right? Like, yeah.
The constant photon will also go on.
Yeah, but like that depends on how log d size and log r size also grows with n, right?
D size can be at most order of 2 to the power n.
Yeah. So log d size is a number between 1.
Order of n.
Yeah. These are all between 0 and n. Yeah.
So you can say that d size of f is big O of r size of f to the power log cube r size of f times log cube.
Something like that. Yeah. So ignoring
That's why the quasi-polynomial is
quasi-polynomial in, yeah. So ignoring log n, this gives us a quasi-polynomial dependence on d size and between d size and r size. Yeah. And this log n may bite us when these are much smaller than log n. This probably renders this useless. For those pathological functions for which log d size and log r size are much smaller than log n, these probably don't give us much. It doesn't give us much. Yeah.
So that is what is the implication of this result? I mean, I see that you have established a relation between d size and r size, and you have bounded. I mean, d size, but I mean that is done in terms of this r size. So is this r size, is it much easier to calculate than this size?
No. So this is an alternative to depth. Size is some complexity measure that is of interest in some situations, and when that is our complexity measure, even then use of randomness does not bring us more than a 4th power advantage, something like that. Yeah.
So is the fundamental question how much randomness helps?
Exactly, yeah.
Complexity of
This is the
how much randomness helps. So this, yeah, so but for these strange functions where these terms are much smaller than log n, randomness can only bring you a polynomial advantage, let's say, fourth power advantage. Yeah.
And then this brings us to the question that, you know, you have to have some constructive algorithm or heuristic algorithm which will give you these random trees.
Constructive algorithm,
If you
yeah.
want to use it.
So we,
This is a theory, that's fine. But suppose people want to actually use random trees, inspired by the results.
yeah,
So we do not have an algorithm for finding the best.
not that I know of. And
Find the random trees, but there are some heuristics to find random trees.
yeah, I don't know. So, huh?
When you try to find some random trees,
Yeah.
there will be some role of L there.
Some role of L there, yeah. Yeah, those are not the questions that we address here. Yeah.
And also, each F is itself thought of as a problem.
Exactly. So this is a slightly meta level question, like, yeah. So,
And designing a T is like designing an algorithm for this,
yeah, yeah.
for this problem. For
So
A could be, you know, any decision problem.
Yeah, it's like sort of like asking, like, given a problem, so do you have an algorithm to find an algorithm for a problem, given a problem, something like that. Yeah.
Or it just means that how to actually choose the best T given a problem. Or
yeah,
you
so-
want me to the probability
yeah.
distribution.
Yeah, so in this work we do not address these questions, we just, yeah, restrict to existence, huh?
If you hypothetically can find the best possible T and then you want B to PL, you will only get in 4th power the
Fourth,
polynomial
yeah.
average.
Yeah. So in the rest of my time, let me tell you a bit about how they prove this result, because yeah, without telling you this, I cannot talk about this. So let me tell you a bit about this, and that will, and maybe I'll point out why those techniques don't extend to this case, and what are the new bits of ideas that we need. Yeah. So the idea is that what Nissan does is he looks at some intermediate structural properties of the function, not of the trees, yeah, that sort of gives us a handle on these numbers. Yeah. So he finds some intermediate objects to which we can relate both D and to which he can relate both D and R, and then he puts together those dependencies and derives his result. So, and those objects are quite intuitive, and also you would have seen them in various situations. So let me tell you about objects called certificates and cubes, and let me tell you what those are through examples. Yeah. So consider the AND function, and it's a 3-input AND function, and let's say this is an input to the AND. This is a string, and I want to convince a verifier that the value of the AND is 0 on this string by showing the verifier as few bits as possible. All I need is to just open the first bit to the verifier, x1 equal to 0, and the yeah. Yeah. So all I need is to show the verifier the first bit and show him that you'll see the first bit is 0, and the verifier is convinced that the value of the AND is 0 irrespective of the values of the other bits. So then we will say, so x1 equal to 0 is a partial assignment. It assigns one of the variables and leaves the others unset. So such an object is a certificate if all the inputs that are consistent with this assignment, on all those inputs, the value of the function is fixed. And for a particular input, so x1 equal to 0 is a certificate of this function and on all zeros, for instance. Yeah. So similarly, let's say this is an input to the addressing multiplexer function. So 0, 1 is the address and this picks out this bit. So the value of the function is 1. All I need to show the verifier are these 3 bits, and the verifier doesn't have any business knowing what the others are. Yeah.
0, 1 will become 0, no?
0, 1, oh, right. So, 1, 0. So I should have written 1, 0 here. Sorry, here. Yeah, so 1, 0, 1 is a one certificate of indexing function on this input. Yeah. So I hope now it's clear what certificates are. The size of a certificate is the number of variables set in it. So size of this certificate is 1, size of this certificate is 3. And for a particular input, let's say x is a, yeah, so certificate complexity of f with respect to x is the size of a minimum certificate for x. Yeah. Yeah. Yeah, and certificate complexity of a function is the maximum of CFX over all x. So it's a max mean quantity. So for every x, you look at a smallest certificate, and then you look at the x with the largest certificate complexity, and that is certificate complexity of the function. Yeah. Now, yeah, so certificates, and what are cubes? So each certificate corresponds to a set of inputs that correspond to that certificate, that are consistent with this certificate. So x1 equal to 0 corresponds to the set of all inputs where the first bit is 0. So this corresponds to the set of all inputs where these bits are set to 1, 0 and 1 and so on. Yeah. And those sets of inputs are cubes. So like if you are familiar with Carnot map, if you plot those inputs on the map, they form a cube. Cells where all the cells are either 1 or 0, depending on whether it's a 1 certificate or a 0 certificate. Yeah. Now CF, yeah, and DF. Do any of you see a obvious relationship between C and D? Can you say that one is smaller than the other or something? Just from the definition. DF must be greater than or equal to CF. Fantastic. So let me, yeah. Because if you look at the leaves of the decision trees, they are certificates. Because when you reach a leaf, you have seen the values of some variables, and that is somehow enough for you to infer the value of the function. Yeah. So this is one way of bounding DF from below. You just show that the certificate complexity of the function is large. Yeah. It turns out that DF can also be upper bounded in terms of certificate complexity. Nissan did it. Yeah. This is one measure. And I'd like to tell you a little bit about another measure, which is, yeah. Okay, let me erase these questions, these portion. Oh, fine. Yeah. So again, let me introduce this measure through an example. So I'll take the example of the tribes function now. Yeah. So let's look at the tribes function on all zeros. Yeah, so there are n bits and there is a natural blocking of square root n and so on. Tribes evaluate to 0 on this input because all the ends are 0 and so on. Now suppose you flip the values of all these bits to 1. Then the function value becomes 1 because one of the ends fires and that sets the output odd to 1. Yeah. We will say, if this happens, we will say that this collection of bits is a sensitive block for this input. Yeah. So a block of variables, set of variables is sensitive if flipping all the variables in that block flips the value of the function. Yeah. Now, what you do is you look at, I want to find out a large number of disjoint sensitive blocks in an input. What is the largest number of disjoint sensitive blocks that I can find in an input? For tribes, I can find square root n. Each one of these blocks is sensitive and they are all disjoint. Yeah. So the largest number of disjoint sensitive blocks on an input is called the block sensitivity of that input. Yeah. And then, similar to certificate complexity, block sensitivity of the function is the largest block sensitivity for any input. So Bs of f comma x is the maximum over x. Sorry, Bs of f is the maximum over s, Bs of f comma x. Yeah. Now, they showed, so this is the main innovation in Nissan's work, this definition. Nissan then shows that Rf is omega of Bs of f. And let me give you, tell you at a very high level the key ideas that go into that proof. So let's consider a randomized algorithm, and let's consider an input having a large number of these sensitive blocks. Yeah. Now, this algorithm, remember, for a randomized algorithm, the guarantee is for every input. So for every input, it must output the correct answer with non-trivial probability. Yeah. So, and now let's say there are some b number of blocks, each of which is sensitive, and I'd like to consider the performance, the sort of the execution of the algorithm on this input x that is under consideration. So once again, so x is an input. It has it has a large number of sensitive blocks. Fx is, let's say, 0, but if I flip any of these blocks, the function value becomes 1. And there is a large number of them. Let's say there are b of them, b of these blocks. Yeah. And now I have a.
So all blocks should be of same size?
No, doesn't have to be. In this case they are, but they don't have to be of same size. Yeah. And now I have a randomized decision tree, and I'm considering running it on this x. Now for the tree to sort of output the value of f with non-trivial confidence, it must touch most of these blocks, right? Because for instance, if it does not touch this one, I can flip this value, function value changes, and it does not realize that. Yeah. So then, yeah, if it happens for most of these blocks, then the randomized algorithm can very.
For example, for tribes, the randomized algorithm say probes one block entirely, and if it is 0, then it knows the answer.
No, but if it's not 0, so for tribes, the randomized algorithm has to query all the variables. Because it doesn't have to probe all the blocks. I'm sweeping many things under the rug. So the right way to do it is through the minimax principle. So and to consider the distribution of inputs and so on. I am sort of trying to give an idea. So it doesn't have to be correct all the time. It can be correct with probability 2/3. So yeah. So it must sort of at least.
So there are two things. One is how many blocks it probes, and the other is in a block does it probe all?
That is right. So that we won't bother about. We just want to say that it probes a lot of these blocks, at least touches at least one bit of a good number of omega b of these blocks. So then that would imply that R is omega b. R of f is omega b, so it makes at least omega b queries here. So you can make this formal. This is, I waved my hand a lot. But so Nissan works this out and shows that R is omega b. So if you can, omega bs, if you can find one input where you can sort of pack a lot of such disjoint blocks, then that certifies that the randomized query complexity is large. Now Nissan also could upper bound D in terms of BS and C, and he puts together everything. So basically this is how it goes. So Nissan firstly showed that Bs is at most order of square root C. Sorry, what did I say? Sorry, C is order of Bs square. This he shows. He just looks at these measures and shows that. Then he constructs a deterministic tree and he then bounds its complexity by Bs times C. And that shows that capital D is at most Bs times C, which is at order of Bs cube by 1. And finally, by this he shows that this is order of R cube. So he has related D and R. And in the process, he also shows that these two measures, C and Bs, are also polynomially related to D and R. These two. No, these are for every function. So he shows that for every function, the certificate complexity is at most the square of block sensitivity.
And that too, RF is equal to omega Bs, that is for every function.
For every function, yeah. So this sort of vague argument that I made here. Yeah. And this construction, so he constructed a deterministic tree for every function and bounded its depth complexity by this, which is at most Bs cube, and then by this it's at most R cube. Yeah. So maybe I'll end by yes, for every total function, like where there is no don't care, that is important. Yeah. Yeah. So that's what, and we showed that D size is at most R size to the 4, like discounting the log n dependency. Yeah. But we cannot work with Bs and C because they no longer polynomially characterize the size measures. So look at the AND function. This is what the tree looks like, right? So the depth of the tree is n, but the number of leaves is also sort of n. So the depth complexity is log n. But the block sensitivity of AND function is n. You just look at the all ones input. All the individual bits, if you flip them, the function value flips. Yeah. So a large block sensitivity does not necessarily imply a large size complexity. Similarly, certificate complexity of AND is full, like n, but the size complexity is small of AND. Yeah. So we looked at slight variants of certificate complexity and block sensitivity and work with them, which I probably don't have time to tell you about.